Okay, I want to make a really quick video that sort of summarizes what you need to know about infiltration. Remember what infiltration is. We have the surface of the ground here. Maybe there's grass or there's plants or there's something up here. And it rains. And as it rains, water is going to penetrate, seep into the ground above the water table. So the water table is somewhere down here. And we have downward movement of water in the soil zone, and that is infiltration. So what do you need to know about infiltration? Well, first, most important thing is you need to know phenomenologically how it changes with time. So if we graph the infiltration capacity, that is the capacity of the soil to allow water to infiltrate with time, we find that it always looks something like this. It sort of starts up high, and then it decreases asymptotically until it reaches sort of a steady state value. So it's initially high, then it decreases over a period of, like, this is usually 1 to 2 days, that it decreases from its initially high value to a steady state value. And theory can demonstrate that that steady state value is equal to the hydraulic conductivity of the saturated soil. That is the number, the variable that describes how easily water can flow through saturated material. So what's actually happening here is, as water penetrates the soil, initially it's unsaturated, but it begins to develop a saturated zone that grows as water continues to infiltrate in the soil. And this zone of saturation moves progressively downward. And eventually we hit a time when the movement of that saturated zone downward is limited by the saturated hydraulic conductivity, and so that becomes the long-term rate infiltration capacity. Remember, capacity is the ability of the soil to absorb water. The actual infiltration rate may be less than that if we're not providing water at such a high rate. For example, if we're providing water only at this level of infiltration, remember this has got units of length per time. If, say, the rainfall rate is only this value here, well, then we can't possibly accept water at a higher rate than that. The water that's accepted by the soil, the infiltration rate of the soil, will be equal to that value there. Okay, so that's the first thing that we need to know phenomenologically. Now, the second thing is to sort of answer the question, why does the infiltration rate decrease with time? And there's actually a bunch of reasons for that, and I'll list them here. First, and probably most importantly, is that as we saturate the soil, as the moisture content, theta of the soil rises due to infiltration, the matrix suction decreases. So remember, for our soil moisture characteristic, if this is N, right, it sort of looks like this. And this is a graph of porosity or void content versus the suction. So when we have low values of porosity, we have low values, this is moisture content, sorry. Moisture content, maximum value here of N. When we have low values of moisture content, lots of air in the soil, then the suction force on the water is really high. And that suction force literally sucks water into the soil when it's unsaturated. So initially, when the soil is unsaturated, it's got a high ability to suck water in. And the reason water is moving downward into the soil is partly because of gravity, and also because of suction. But that suction force decreases as the soil becomes progressively saturated, and eventually when it's completely saturated, the suction force is zero, and then the only force moving soil further into the soil is gravity. So what happens is, initially there's a high suction force which causes relatively high values of the infiltration capacity until the soil becomes saturated. Now, the second reason has to do with the actual structure of the soil. If we actually were to look at the distribution, the geometry of solids and pores in the soil. If we do that, we find that, and soil scientists have described this in great detail, is that soil is typically made up of things called pedons, which have structure. So these pictures on the left, these these diagrams show the various types of structures that occur in soils. These structures are a result largely of surface tension causing the solid material, especially the organic material, to clump together. And as they clump together, that produces spaces between the clumps, which are pathways for relatively rapid infiltration. So the more structure a soil has, typically the higher will be its infiltration capacity, because there will be larger openings through which the water can flow. The photo on the left shows a structure with a sort of soil with an aggregated structure, and you can see the clumping has resulted in clumps like this guy here. Okay, there's one clump, and there's another clump, and between these clumps are areas, space where water can flow. So as we wet the soil, a couple things happen. Most importantly now, well, number 2 is here, as the soil moisture content increases, the clumping decreases. So the structures become less well defined. And that's simply because the clumping is held together by surface tension. And of course, the surface tension forces decrease as the soil becomes increasingly saturated with water. The second thing that happens is related to the fact that as water bombards the surface of the soil, it pushes around fine material, and the finest material, we call the fines, the clays and the silts, often get packed or relocated into the channels. They get pushed into those openings, into the channels, and block them. So this is typically what we find, is that the finest material will be washed into those channels that were otherwise the high velocity pathways and clog them up, therefore decreasing the infiltration rate. We also could have, in some soils, there are certain kinds of clays which, when they get wet, they expand. So if we have expandable, they're called expandable clays. They're a specific type of clay mineral. Then these will expand when wet and further clog openings, right? So if we just imagine clay particles swelling, and the openings around them therefore decrease in size and clog openings. And there you have the main reasons why what we always see when we see an infiltration event is that the initial infiltration rate is high, and with time, as those processes take over, the infiltration rate decreases until we get to a long-term average that is equal to the saturated hydraulic conductivity, K sub S.